All right, everybody. In this lecture, we're going to be talking about different loss functions and comparing them to each other. Specifically, we'll start with a recap of empirical risk minimization from last lecture, and then we'll look at several loss functions and see how they are affected by outliers, and kind of use outliers as a way to indirectly study the three loss functions. And then we'll see how center and spread, so mean and variance, what their role is in these loss functions, and we'll try and build towards the overall idea of moving into linear regression as a more complex model from the constant model that we've been using. Remember, the constant model has just one parameter, which is the prediction. The linear regression model, even the simplest case, will have one parameter that we can kind of mess with as well as the prediction. So let's do a quick recap on empirical risk minimization, just so that we're all on the same page. If we think back to the last two lectures, we had this data set. We were looking at a person leaving from their home, going to school or work, and they want to see how long their trips took in minutes, and depending on when they left home, their trip could vary. And from that data set, we have this very simple kind of toy data set of these 5 values, 72, 90, 61, 85, and 92. And the goal so far that we've been trying to look at is, from this small data set, what's the best prediction that we can kind of create or determine from this data. And best really depends on what our definition is. We found that both the mean and the median under different conditions can be the best H star that we get when looking again at the constant model for this specific data set. So for best, we had mean and median, and we'll explore those some more today. And then it's important to also remember the 3-step process towards the modeling recipe that we have. So in this case, we had the constant model. So we have our hypothesis function, h of x, and that gives us some sort of h. Of course, we're looking for h star, which is the best h. And we determine the h star by taking a loss function and then minimizing it. And the 2 loss functions that we have been looking at so far are loss function of squared h, and that just equals yi minus h squared. And this, of course, the yi being our actual data, and the h being our predicted. And this would be the squared loss. And then we also looked at the absolute loss. And that was just the absolute value of yi minus h. And from both of these, squared loss and the absolute loss, we minimize both of these by the process of taking the derivatives, setting it equal to 0, solving for it, and finding what that h star was. And we concluded that for the squared loss, it was the mean, and for the absolute loss, it was the median. So we have this function, r squared of h, and we determined that that was 1 over n, the summation of n plus 1 for all of your yi's minus h squared. So that is for all of your data points minus h. In this case, h is always going to be a constant value because, again, we have our constant model where h is always the same regardless of what the y's are, what your data is, and that simplified into us determining that h star, or the best h, minimized h star, was just the mean. This is y1, y2 for all of youryn's. And then for the absolute value, r absolute of h, again, 1 over n, and we're going to be summing up all of the yi's minus h for our entire data set. And from that, we found that it was just the median. So that was h star. Yeah, I can make these just the same. Okay. So this modeling recipe is something that we will continue to do throughout this course, and specifically in this lecture as well. So what does that mean exactly? Well, we found that through the minimization, the empirical risk minimization, which is just another way of saying minimizing for average loss, we're taking this, in the case of squared loss, the squared loss function, and we determine the empirical risk by solving for this equation here and setting it to 0. And we do the same thing for absolute loss as well. So it's a pretty straightforward mechanism that we do to determine this h star. And in general, this approach applies to any loss function where what we're trying to do is minimize the average loss for that loss function across or over all of your data. So this loss function here is generalizable as long as you're trying to do the empirical risk minimization or average loss minimization. So in order to do that, you have any generic loss function over all of your data, and then you take the average. And that winds up giving you the average loss for this generic loss function. So this is kind of just a very quick recap of what we did last lecture. Just to jog your memories, if you have any questions, feel free to post them online and we'll get to them. But let's go ahead and get started on the kind of meat of this next lecture. Okay, so let's go ahead and look at this question. You can go ahead and pause the recording now and try and answer it. What we're looking to do really is, let's draw this. So here we have mean squared error. And from now on, whenever I put MSE, that's the mean squared error, as well as mean absolute error. So with mean squared error and mean absolute error, are one of the following statements true? So for any data sets and any prediction H, if you square the mean absolute error, right, that is, if you square this entire thing, do you just get mean squared error? So if you square mean average error, is this what you get? And either that's true for any prediction for any data set, or it's sometimes true, or true for some cases, but in general it's not, or there's never a case where we can say this is true. So go ahead and pause the video and think about it a little bit, and we'll come back and try and think through the answer. Okay, so let's go ahead and try and think about this for A. It's true for any prediction in any data set. So let's go ahead and start by, let's just expand the summation for absolute error. And if we have, as we do up here, okay, so if we go ahead and expand it and take it to the and square it, what do we wind up getting? Well, it is true that we have some constant out here, 1 over n squared, and we get some things in this that do resemble mean squared error. So we'll have some stuff that's like y1 minus h squared, but we're also going to get other additional terms that we don't really want to see if we're trying to say this is mean squared error. So times 2 minus h, so on and so forth. And we'll have other stuff in here too. But really, because of stuff like this, we're going to go ahead and say that this is not equal to mean squared error. So it's the case where in the general term, this is not true. So we can cross A out. This is generally not the case. So let's look at C. Is this never true? Can we find some case where squaring the absolute value does give us the same thing as mean squared error? And in a very trivial case, we can find that it is true. So we know it can't be C. And the case where it can be true sometimes is if you have one data point. So it's true in some cases. B might be, it's true for at least one H for any data set, but not in general. A little bit of a strong statement, but we do find some truth in that. So in this case, B would be the best answer here. And one way to think about that is, if we have the graph where we have mean squared error, let's do that in green. So we've got some sort of mean squared error, and then we have some sort of, if you remember back to the graph that we made for mean absolute error, that was sort of like a piecewise linear function where we had these kind of individual line segments with corners, where each corner is where the data was, so the y's. So we had something that was kind of like this. And that, in this case, there's an area where these two functions would overlap. And so there could be, under some cases, that we see that there's a similarity when you do square absolute value. But in general, it's not the case. And we can find at least one easy instance where it is true. Again, when there's just one value or one data point. So in this case, B is the answer that we would say is most correct. Okay, hopefully this gives you something to kind of think about. But moving forward, let's go ahead and begin to talk about how do we actually choose a loss function. Okay, let's go ahead and start looking at how we decide between different loss functions, and we'll do that specifically by trying to analyze the difference between the mean and the median based on the underlying data that we have and how our choice of one of those impacts the optimal prediction, or the H star, and really which H star for either the mean or median winds up being better. So this is going to build some intuition for that. So let's continue on with our toy data set of 5 commute times. And we want to look at these two things right here. Median for this, okay, so for this data set, our toy data set, the median is 85 and the mean is 80. So let's pretend that we added 200 to our largest commute time of 92. So 92 gets turned into 292. So let's think about what happens. What happens to the median? Well, since the median still has 5 values, it remains unchanged because 85 is still the middle one. So the median remains unchanged, 85. So the same. But what happens to the mean? Well, we add 200. So in effect, so let's do the simple math real quick. That would be taking up y1, y2, all the way to y5 and add them up. So y1 plus y2, y5 divided by 5 is going to give us 120. Now, new mean is 120. Old mean is 80. So right off the bat, we can see just how much more the mean has increased by introducing this. We can call this for now an outlier. But really, when we think about what has happened, we haven't just increased one value and thus the mean has gone up. By doing this, we've kind of increased the average of all of the data points. And what I mean by that is if we take, let's say, the old mean, which is 80, better. So we have 80, which is the old mean. And we go ahead and add 40. We'll get 120. Where does the 40 come from? Well, the 40 comes from the fact that we added 200 to the data set. So we added 200 right here, and 200 divided by 5 equals to 40. So it's not that this value of 40 is important for anything, but conceptually what I want you to understand is that by introducing such a large outlier, so increasing this by 200, it's essentially like we've increased the total average by 40 across all these data points now. That is affect what is kind of happening because the mean is 120, which is, slightly less than 40, but a little bit, much more than the median of 85. So one good way to think about this is to, let's take the data set and put it onto a number line. And let's see, this is yellow, so we'll use our yellow. Let's think about how far away things are from the mean and median. So let's say that we have this value of 4 here, and this 4 is RH. It's just a prediction, right? It's not H star, it's just a prediction. And what we want to do is we want to see how far all four of these values are from our prediction. And this data set is not the same as the previous toy data set. This is a new toy data set. So we have Y1, 2, 3, and 4. And these are at value 1, 2, 3, and 14. So if we make our prediction using, again, the constant model, and we say H is 4 for this data set, then how do we kind of encapsulate this idea of loss? So 3 is 1 unit from 4, and Y2 is 2 units, and Y1 is 3 units, right? Not very difficult. What about Y14? Well, Y14 is 10 units away from it. So if we're using the mean absolute error, this is in effect our total loss. We'd sum up the 10, the 2, the 1, and the 3. What happens though if we think about squared loss? So in the case, and let's particularly pay attention to the 14 and the 3. So if we look at squared loss, well, 1 is just 1 squared, and this 14 is now 10 squared. So what is this telling us? Well, what we're saying here is for our two loss functions, absolute error and squared error, for absolute error, the magnitude of the difference is 10 from this data point to our H of 4. But with the mean, or with the squared loss, it winds up being 100, which is 10 times greater than with the absolute loss. And also, something else that's really interesting to note is that the penalization for being 1 unit off with squared error versus being 10 units off is 100 times greater. So what does that translate to? Well, the squared loss adds a ton of loss, like numerically, to your total loss when you have an outlier. And in this case, we can agree that 14 is most likely an outlier in this extremely simple 4 data large, 4 unit data large, or 4 pieces of data set. So let's go ahead and kind of compare, see what this looks like when we talk about the median and the mean. So let's get our green. Okay, so in this case, 5 is the mean here. And we have the median, which since we have 4 data points, the median is going to be in between Y2 and Y3. So it'll be in between here. And the median, of course, can take the range of values, any value between 2 and 3, and that minimizes it. And what we're saying is that the median, in this case, 2.5, and the mean, in this case, 5. The mean is being pulled towards the outlier. That is to say that this value of 14 for Y4 makes the mean extremely sensitive. We could put really any value that we wanted for Y4. Y4 could be, 10,000. And the median would still be 2.5, but the mean would be greatly shifted over, to some number way out there. but the median would still be 2.5. So this is kind of what we're talking about when we say that the median is robust to outliers. It doesn't really matter. All that matters is how many numbers are on each side of the median. In this case, 2 on the left, 2 on the right. So y4 and also y1 could take on whatever value. Y2 and y3 and the area between those two will always be the median. The mean, though, gets shifted drastically based on these kind of extreme values, these outliers. So while the mean is easier to solve for because it's differentiable, and we've seen we get some nice stuff with the squared loss function, it is very susceptible to outliers. And what that means, kind of like in a data science or pragmatic point of view, is that it's really important to watch out for outliers and to kind of take care of them and make sure that the extreme values in your data set are there because they're supposed to be there and they're not artifacts of outliers. So this is kind of what you want to think about. And we can look at it with a histogram. That sometimes can be a good way to look at it as well. So in this case, what do we use for colors? Mean was purple, mean was green. So if we have the medium here, that's going to be something around 70. And the mean would be somewhere around here. So we have these values for commute time, right? And there's this histogram which skews to the right. One way you can remember this skews to the right is there's lots of little tricks that people use. Beyond just memorizing it, one thing you can think about is if you've got like a wad of bubble gum, and you kind of, now it looks like a happy cloud. It's a happy cloud with that's a wad of bubble gum, and you're to take that piece of bubble gum and kind of pull it out and kind of stretch it out into another little piece out here. Kind of looks like an action or a neuron now. You're pulling that piece of gum to the right, and that kind of creates a thought in your mind of a right skew. But it's just easy to think about it as wherever the extreme values are, like this. There's a slope like that. This is a kind of slopes down. That's a rightward skewed histogram. But anyways, in this example, we see this value of out here, and this is the value that's greatly pulling our mean over. Without that, the mean might be somewhere over here. And so when you're doing this type of data analysis and trying to determine what types of loss functions to use or how you're going to build machine learning models, great care needs to be taken looking at your data set, because is this an outlier? A real outlier? And if it is, maybe it shouldn't be in this data set, we should remove it. But extreme values in data sets occur all the time and for perfectly good reasons. So you really want to make sure that you're not just removing things that look like outliers, but you're doing an analysis to determine if it really is an outlier. And some real world examples of that might be like, for example, income. And these income distributions, it's very easy to see how the high earners wind up kind of, I don't want to say artificially, but they definitely skew the mean of income for an area to the right. And so if we, real quick, going back to this slide, one of the nice things about the median is that we know that all the values to the left of the median here equal the number of values to the right of the median. So the median gives us a nice way to think about like the true, I don't want to say fair center, but the center that provides us a nice view into perhaps where the true the true midpoint of the data is. So for income, if we look at like the United States, we see for the median, it's around 35K, but for the mean, it's up to 60K. And there's this kind of artificial pulling of the mean out to the right because of so many, high earners, people, and I don't mean like, people making 400, 500,000. Of course, they pulled out the mean out as well, but you have the people who are making hundreds of millions of dollars a year, and that regardless of those people being such a small amount of the population, they really do pull the mean out quite a bit by themselves, because the mean is very susceptible to these kind of extreme values. So we want to make sure, just like when we're doing data analysis and exploratory analysis, we're creating these kind of plots when we're looking at machine learning and trying to figure out how do we determine the correct loss function to use and this type of stuff. We want to be very cognizant of the underlying data and trying to get a handle on what's going on with it. Okay, so one really good way to think about mean and median is that they're acting kind of like balance points. Maybe if you have a like a seesaw or something, and you have kids that are playing on the seesaw, and it can go up or down. It's where is this balance point here, and the mean and median both work in different ways to act as balance points. So the median, for example, winds up being tremendously easy because it's just the number of points that are below and the number of points that are above, and you're equalizing or equating them. So in this case, we got 2 below and 2 above, and that's why the median can occur anywhere between these two values of y2 and y3, in this case 2 and 3. So that winds up being very easy. Now for mean, there's a little bit more to it. However, of course, it's easier to calculate mathematically, but we have to kind of think about this a little bit differently. We're not just counting the number of data points that fall below or above some value or range of values. But what we're really trying to do is think about sort of the spread or the distance that each point has to the value that's the mean, in this case 5, which would be the H star for mean. And if we look at the kind of distribution of these 4 numbers, or these 4 data points, y1 to y4 from 5, we can kind of see where they wind up equaling 0, which is the main thing. So let's go ahead and say we've got the distance from 5 to 14, and that's going to be a 9. And we have y1, y2, and y3. y3 is going to be -2. y2 is going to be -3. And y1 is going to be -4. And then what happens if we sum these all up? Again, look at what's going on here, right? It's the sum of all of these data points, the yi's, which in this case is y1, 2, 3, and 4, and we're subtracting from those our h, 5, and in this case 5 winds up being the mean, so it really is H star. But this 5, when we subtract it from all 4 of these y's, we want to find out if it's 0. If it's not 0, then we don't have H star, we just have H. When we find H star, it will equal 0, and we can show that here by taking the values, and we see that -4, -2, -3, and 9 cancel out, and it winds up being 0. So we have -4, -3, -2, and 9, and this just winds up, giving us 0, which is why 5 in this case is our H star. It is the one that takes the sum of all these differences and sets them to, and wind up getting 0 from it. So another way that we can kind of write it is it's the sum of the distances below and the sum of the distances above our H. So we can more formally or mathematically write it as, and maybe we can take this and move that there. We can write it down here as the sum of the points where yi is less than h, and this is yi minus h equals the sum of where yi is greater than h for yi minus h. So we're essentially just doing this for the points where they are below and the points where they are above. And if that equals 0, which in this case it does, then that gives us our H star. Now, there's interesting to think about here is, we have these different types of loss functions. We have our, absolute, which we found as the minimizer being the median, and for squared loss, we have the mean. And of course, these are both solved by doing the process of taking the derivative and setting them equal to 0. And this is what we've been doing over the last several slides, last 2 lectures really. And this is written in just a little more of a general format, but it's similar to what we've been looking at, just the number of yi less than h. We set that, we give it a 1, and when it's greater than h, we give it another 1, and then we can take those sums and set them equal to 0 and figure out. But really, this is what we've been doing, and this kind of begs the question of, why stop at squared loss? Why don't we go on and do more things, to the third, to the fourth, the 100th? What's really stopping us? Why wouldn't we, or why would we want to do that? And also, if we do that, what happens to the minimizers? And then, honestly, the derivative part and setting it equal to 0 doesn't really change. That you do, but these minimizers wind up being slightly different as well. These also become slightly more complicated to solve for. We can take a look, for example, where we have yi minus h cubed. And the reason why we use the absolute value here is not because this is mean absolute value anymore cubed, but in order to cube it, we're going to have, like you could, in this case, have some, negative values to the third, which would give you, a negative number. So we just take the absolute value of that to get rid of those, because remember, we don't want to, when we're doing our loss, we're summing, and we don't want to be summing with negative and positive values. We want to be summing with either or, but in this case, positive values. And as well for the fourth, right here, we could also solve for this by just taking the derivative and using the product rule, and this would give us -4 nth over we're summing up yi minus h, and this just goes from fourth to a cube. And then we're going to want to do that. We'll set this equal to 0, and we'll solve for it, and this is how we'll find the minimizer. And this minimizer specifically wants it being very close to the mean, not necessarily the same, but pretty close. So there's lots of different loss functions that we can kind of explore. And specifically, we're going to look at a lot of these over the these next several lectures. But we really want to think of the idea of a generalized way of thinking about this. Okay, so remember now that the main point of what we're trying to do is to pick the best H star, that is the prediction for the constant model that we've been working with. And we have lots of different ways of doing that. We can do the mean absolute error, right, which should be this right here, or the mean squared error, which would be right there. And in those two cases, we're always thinking about these ideas of balance points. So the mean absolute error balances it so that H star winds up being in the middle of the data, so that you have the same number of data points on the right as there are data points on the left. Whereas the mean is trying to minimize the sum of Euclidean distances on both sides of the mean such that it equals 0. So these are just two ways of trying to find some sort of balance in the data set, and then using that balance point as the H star, or what our prediction is going to be. So that kind of begs the question, there could be other better potentially balance points. And we can kind of explore these a little bit and try and quantify some of them. One interesting question that you might want to ask is, well, what happens if we start raising these empirical risk functions to different powers? So, we have to the third, or to the fourth, or to the 100th, or, even higher and higher, maybe to the 10,000th, or to the, infinity power. So let's kind of think about that idea for a little bit. In order to explore that, we're going to create this idea of like a generalized loss function. So that's the LP loss, where this P we can set to whatever we want. So if it's, to the power of 2, we're talking about the, squared loss. And we want to talk about this in terms of H. So we set it equal to this function here. And then we start trying to kind of play with this idea of what P could be. So when P is 1, we get the median, that's mean absolute error. When P is 2, we get the mean, that's mean squared error. And we can kind of start to plug in more and more P's and see what happens for, a given data set. So that's what's happening here. We have this sort of new toy data set that we're working with. And that would be 1, 2, 3, and 14. And the main thing about this data set to think about is this idea that we have an outlier over here, right? Or we have some extreme value, and then we have some grouping of values. And as expected, with the mean absolute error, which should be right here, we have something that's like 2.5. And with the mean, we have something that's at 5. And so what's happening is, and this is from like maybe an intuition point of view, is as we increase P, right, from 1, and we increase it to 2, so from mean absolute error to mean squared error, there's this rightward shift in what H star should be. And so if we kind of run this through a for loop and keep adding in a different number of p and iterate it, one at a time, we can draw this graph over here. And on this graph, the x-axis, we have p, and on the y-axis, we have this h star. So what the resulting h star would be given some p value. And let's go ahead and look at the mean absolute error. So this would be mean absolute error. And we see that mean absolute error, we know that p is 1, right? We got that from over here. So if we're at 1 and we see that it is 2.5, so that's 1, 2.5, that's right here. And this is the mean absolute error, which also winds up giving us the median of the data set. So this is the median. So let's go ahead and make p be 2. So here we have mean squared error, which is 5, or the mean. And if we go over to 2, and we go up, we see we're right here. This is 2 and 5, and that's the mean squared error, which is the mean. Okay, so we plug in more p's and more p's and more p's, and what happens? Well, we see that the plot continues to go up, up, and up, and then it stops at a certain point. The point that stops at is about 7.5, and then it levels out and it goes on for forever. So as p's increase up to a certain point, that point being h star equals 7.5, it doesn't matter what value of p you put in. So the intuition here is, as I add more and more p's, I get closer and closer to 14, right? That's maybe the intuition, because as we increase p's, and you even see from this chart right here, we do tend to get closer to 14. But remember, we really can't get all the way to 14 or even close to 14 because, again, we're still talking about balance points. And so even though we're getting closer to 14, there's still this idea of a balance point. And if you had some sort of h star that was over here, there'd be a short distance to 14, but there'd be these long distances from y1, y2, and y3, and there's just not enough balance there. So while mean absolute and mean squared both have different balance points based on how what your view of the data is, that's more of maybe a philosophical idea in terms of how do you select the best minimizer, and that's based on the problem you're trying to solve. But like mathematically, this will never get close to 14. It can get closer, but it will never be closer to 14 than it is all of its other data points. There's just not enough balance there. And so there's one pattern you might see here, 7.5, and you might say like, oh, well, 5, 2.5, 5 plus 2.5 is 7.5. And that's just because of this example. The mean squared error, h star plus the mean absolute error h star equaling 7.5 is not something that you should think about. That's just due to chance. But what we do want to see is this idea of 7.5. Where does that come from? Why is it when we have p as it approaches affinity, right? So the limit here. Why is that 7.5? What's so special about this, and why doesn't it ever go higher than 7.5? Right? Because this never goes any higher. It stays at 7.5. So what's doing that? Why does it do that? And to really understand that, we have to think about where 7.5 comes from. And where 7.5 comes from is something called the mid-range. The mid-range being you take the largest value in your data set, this case would be 14, and you take the smallest value in your data set, in this case would be 1, so the two extremes, and then you just find the midpoint between those two. So what we can say is if the median, if the median minimizes absolute loss and the mean minimizes squared loss, the mid-range minimizes average loss as loss approaches to infinity. So as we go higher and higher in p's right there, or as we go higher and higher in p's going this way, what we see over here is the mid-range. So another way you can phrase it is this is the technically the mid-range minimizes infinity loss. So this would be like that's what we can call this. Now, I mean, infinity loss just happens to be because we have the limit here, and that's what we also see on that chart. This isn't like the next new Marvel movie or anything, right? Where you have right. This is so maybe one funny way to think about it, but and that's a terrible rendition of Captain America's shield, but the idea here is the mid-range at its extreme only really cares about, or the mid-range as a minimizer only cares about the extremes in your data set. It really doesn't care about any other data. Like we could have any other numbers of data here. Like it doesn't matter how much data we have. The mid-range only ever cares about these two extremes. Whereas we saw the mean cared a lot about the data, but also outliers, the mean squared loss, and the mean absolute loss cared a lot about like how many points of data were on both sides of it. But the mid-range only cares about your two extremes. So it's kind of like agnostic to any other data in your data set. And is that like a good loss function? Is that something that you want to be able to capture in your, for example, in this constant model? And it depends, right? That's where the philosophical question comes in. Like, what is the problem you're trying to solve? Do you care about the extremes in your data set? Is that what you want to be sensitive to? Do you care about outliers? Do you care about, clumps of your data? And as you get more into data science, machine learning, these things will become easier for you to answer, and you'll have practice picking good loss functions to use. But it often really just depends on what the problem is and what the data set you have is, like what constitutes your data set. So let's go ahead and think about this maybe in one other way too. I think it might be important, and that's like worst case scenarios. So we have these three colors here, so let's use them. So purple, we know that's already mean absolute error. So we have maybe we'll start with let's start with mean, because that has the it doesn't matter. We'll start with the median. Okay, so mean absolute error, which its minimizer is the median, and for that the median in this data set up here, remember 1, 2, 3, and 14, this is at 2.5. So mean equals 2.5. So what is the data point in this data set that's furthest away from 2.5? Well, that'd be 14 over here. So the worst case distance from 14 to 2.5, right, that's going to give us 9. So if because we can go either direction, we'll take the absolute value. So that'd be 14 minus 2.5 equals 11.5. So at worst case, your H star is going to be 11.5 units away from the maximum value in either direction of your data set. In this case, it'd be 14. Now, if we look at the mean squared error, that'd be the green one here, and that looks at the median, that's going to be 5. So, and its worst case distance is going to be 14 minus 5 equals 9. So the mean's worst case distance from the most extreme data point would be 9. And then the mid-range here, so there's not a fancy acronym for mid-range, is going to be 7.5. And its worst case, there, no misspelling. Oh, got me over there. Would be 14 minus 7.5, and that's going to give us 6.5. So the worst case distance for the mid-range is 6.5, right? So like the longest distance is going to be that and your 1, because we know that the mid-range is the middle point between your two most extreme values in your data set. Whereas the mean's greatest distance is going to be to this outlier, and the same thing for your median as well. Like that, those are the worst case. So why does that matter? Well, we have a very simple model, which is the constant model, which is what we've been working with, and we'll get into more complex models later. But H star is going to be the one value that we use to predict. So if we have these 4 pieces of data here, right, we are going to learn some sort of function that we want to use to make a prediction in the future. So we might say, we might get a new piece of data in the future, and we're going to still make the same prediction. And so what we're saying is, by looking at these 4 pieces of data, that, if this was like some real world data generating process, and we were going to expect to get a new number, our expectations might be that it's probably going to be somewhere closer to these 3 than to this one, right? Because we have this cluster of data here. And so maybe this was an error, or maybe it was a true outlier, or maybe this really is the range. But our expectation, our feeling from looking at this data is that it's probably going to be somewhere around here. And so we look at these 3 loss functions, right? The infinity loss coming to a theater near you, or mean absolute error, or mean squared error. Like, these are all different loss functions that we can use. And so in this scenario, we might say that mean absolute area might give us the best model, right? If we're going to take the median, this might be the best prediction that we can make going forward, is always to just pick 2.5, because this tends to be where most of the data is grouped. If we really believe that this is a true outlier, like 14. If we don't think 14 is a true outlier, we think that the range of real data does go from like 1 to 14. And maybe we just have these 3 that are close together, but we're expecting that we could see some more data around here and here and here and here. Then maybe it might make sense to go with the mean, because we're sacrificing a little bit of being close to this grouping to take into account the 14. And so the mid-range might go a little too far for our taste. And so really how you select which one of these is truly best, right? Because they all minimize, but which one you select to choose as your H star is completely dependent upon the problem you're trying to solve and what in your data you think are true outliers, right? If this is a true outlier, like this is an error, this data, like a sensor was failed or something, and this is the data we got, then we could just throw this away. And quite frankly, at that point, this data is so close together, it wouldn't matter which of these 3 we probably use. We pick the one that's differentiable, like the mean, because it's the easiest to calculate. But, once you have more, like, the reason why we're doing this is because we're kind of looking at these ideas at a mathematical level in a highly constrained environment, so you can kind of see how they behave. But in a real world problem where you have tons of data, hundreds of thousands or thousands of observations, and you have complex models that don't just have like one parameter, like an H star, but we have many parameters, like linear regression model that has many, many parameters in high dimensional space, these things become a lot more complicated. And so we want to rely upon the intuition that we're building here with the math to be able to make good decisions. So this is why, we're going through this kind of stuff and thinking about these loss functions and seeing how they behave. So hopefully that adds some context to all this. So we'll go ahead and next look at a fourth type of loss. So we had mean, squared error, mean absolute error. Those are two very real loss functions. This infinity loss is more of a, you wouldn't really use this probably, like the mid-range as much, as it's not very common at all. But this is like a good theoretical understanding of loss functions. But the 1.0 loss, we'll see what that looks like next. All right, so let's go ahead and look at this final loss function. This is called the 0,1 loss. And in this case, what we're trying to do is say that for any value in our data set, any yi, we're going to look at whatever our prediction was, h, and we're going to assign a value of 0 or 1. So you can kind of think of this as an if-else statement. If your data equals h, assign 0. If it doesn't equal h, assign 1. And we're going to sum those all up. And remember, 0 is what we want because we're trying to minimize loss. We want the lowest amount possible. So if your prediction does not equal a point in the data set, then we're going to penalize and add 1. And we're essentially summing all these zeros and ones for any given h, and we're going to find the average of them. Remember, empirical risk, the average loss. So this is the average 0,1 loss of the summed 0 and 1s. So this is an interesting loss function, and you'll kind of see how it ties into the mean and median and mid-range very soon. But before we jump into that, let's go ahead and try to answer this question. So we're given the 0,1 loss, and we want to try and, for this data set that's n large, so y1, y2, yn, and suppose that each of these values in the data set are all unique. So there's no duplicate values in your data set. What is the 0,1 loss for y1? And I suppose it could be for any y, but specifically for y1. So go ahead and pause the video for a little bit, and we'll then work through what the answer is going to be. Okay, so let's go ahead and try and answer this. And this is not very difficult or tricky, but the whole point lies in the fact that all the data points are unique. So what the 0,1 loss function is kind of asking you when you're summing up these 0 and 1s and finding the average is it's really another way of saying the proportion of so it's the proportion of points not equal to h. So that's kind of what 0,1 loss is trying to identify. And specifically for 0,1 loss, if we guess for y1, it's really the proportion of points that are not equal to y1. So what does that look like? Well, we know we have n data points, right, from right there. And since it's a proportion, we care about doing division here. So we have n, and we know that we care about one data point in particular, so it's just n minus 1. And that's going to give us C as the correct answer. All right, so let's kind of dive a little bit more into 0, 1 loss. How do we go about minimizing it? Well, let's think back to the data set that we had before. So that was 1, 2, 3, and 14. And let's think about what this loss function is asking us. So for any h, if that h is equal to yi, and these are, our yi's over here, and our h, any h we choose really, we can test, but if we choose 1, we have h is going to be 1 when it's 1, 0 for 2, 0 for 3, and 0 for 14. If we were to choose 2, it'd be 0, 1, 0, 0, so on and so forth. So we're trying to, again, find the proportion of points not equal to h, right? This is kind of the plain English version of what this loss function is doing. And so if we want to minimize, so let me write this down maybe. So if we want to minimize yi equals h as much as possible, then what do? Well, we just mainly set h, in this case is be h star, to the mode, right? Because every time yi equals h, we have 0. So we want 0. We want to be as close to 0 as possible. So we can get the most amount of zeros if we set it equal to the mode. You might be saying like, well, yeah, that's true, but in this case, if we don't have a mode, we have just 1, 2, 3, and 14. They're all unique, and that's true in this case of this toy data set, but that is often not the case in a real world data set. And just as an example, if we also had here like 3 again, and we did it for 1, 2, 3, and 14, right? For 1, it would be, we have 1, 2, 3, 4, we have 5 values. So it would be 4, 4, 3, because it's 1, 2, 0, 3, 0. And for 14, it would be 4. So in this case, the value of 3, minimize loss, it gives us 3. So that's why we set h star is the mode. It's the most common value, specifically in our data set for y1, y2, all the way to yn. Okay, so this is a very simple loss function in that case, but it just goes to illustrate that all these loss functions so far, we have L squared, L absolute, value L infinity, the L infinity being more of like a conceptual or philosophical idea of a loss function, and then 0, 1 loss. All these things really, well, one, they're summary statistics, but they talk about the center of the data set in different ways. They're trying to find different balance points in the data set. They do that by straight counts, for example, in the mode or the median, or they do it by simple midpoints, for example, the mid-range, or they do it by trying to minimize some sort of Euclidean distance between the two sides of the data set, like with, for example, the mean. And these are all really good things to think about, because from a theoretical understanding, as you get more complex machine learning models, we're always trying to understand better what the loss function is doing. How do you find those patterns in the data set? And we look at this idea of robust outliers, always unique, differentiable. There's all trade-offs in these kind of loss functions. I will say in practice, the mean tends to be the one, for the most part, between at least all these, is the one that's used, mostly because it's differentiable. And while this is the constant model, any complex kind of model, being differentiable matters a lot. It makes the calculations much easier. So, and the robustness to outliers isn't that big of a deal for the mean in practice, because you can really, through the practice of exploratory data analysis and an outlier analysis, you can remove a lot of pesky outliers from your data set anyways, which makes this robustness to outliers issue of the mean squared error not as large. And certainly the trade-off for it being differentiable is, and also being unique, is very great. I remember the reason why median isn't unique, and potentially mode, because you can have, as we saw in the last data set, multiple numbers that are the mode. But for the median, the mean absolute error, when you try and minimize that, if you have an even number of data points, it winds up becoming the minimum, anything in between the two middle numbers. So just to kind of recap, if you had 1, 2, 3, and 14, the median could be anything between 2 to 3, like 2.007, 2.5, 2.9, so on and so forth. So that's what we mean by it's not always unique under certain conditions. As these all minimize it. So these are just a good way to really dip your toes into the idea of minimizing, and trying to find out what the best possible prediction could be for a given data set. All right, now that we've kind of looked at these loss functions, let's think a little bit about center and spread and how these loss functions relate to the center and spread of the data set. So for a loss function, we see that H star, which minimizes, for example, a constant model, that H star is a measure of the center of the data set. So the mid-range, the mode, the median, the mean, these are all talking about the center of the data set. But the output of the function R of H star, what that outputs is really some measure of the spread. And this is an interesting concept, and I think it's a nice way to kind of close the loop on sort of what's happening and why these ideas of center and spread are intrinsically tied together when it comes to these loss functions. So let's think about squared loss first. So what's happening with squared loss? Well, when you minimize square loss for your data set, you get this H star, which we found time and time again to be the mean in this case. So what happens if you take this mean that you found, this H star, and you put it back into this equation? What do you get? So that's what's down here, right? We've taken the mean and we put it back in for H. And something really interesting happens. What you get out is the variance. So another way to think about this mean, right here is the idea of like you would probably see it written normally as that'd be 1 over n sum 4y minus. So you'd probably see, this y bar there, but it's just another way of saying, the mean for a data set. And of course, this is the average. So what can we say about kind of like the mean? Well, the mean, of course, is the spread of the data. Well, the mean itself here is the squared distance from the mean. We have this square here. So what this is really telling us when we put the mean back into the equation is we get out the variance of the data set. And that's this right here. So the average of the data, so the average of the sums of your data minus the mean is just the variance of the data set. And if you think about like where the mean is, so we can, we have our examples of like y1, y2, y3, and y14, right? We said that the mean was somewhere around here. Then the variance that's captured in here is these distances, right? That's the spread of the data set. And so we can get that spread of the data set, or the variance, by plugging the mean, which is our h star, back into the equation for the mean squared error. And that's kind of like an interesting little result that shows how these are all kind of tied together. And since we're dealing with the mean, we're not always guaranteed to be in the same units. So if you take the square root, we get the standard deviation. That brings it back into the unit of measurement that we care about for the data set. But this is just like a nice little thing that we can see. It's an interesting result. And if we take, and this is our original data set that we were working with at first, is 72, 90, 61, 85, and 92. If we take that original data set and we have here we graph the function for the mean squared error, then I believe the mean for this was 80. So that we'll use maybe red. So that would be right here. So this was h star equals 80, which was the mean. And this makes a lot of sense, right? When we're kind of optimizing this function for loss using the mean squared error, we get 80, which is the mean. But what about, how does this function shift? Where is it located in relation to the y-axis, which should be, for an h? And that seems to be, which is, we'll use orange right here. So 130 maybe, something like that. So really the vertex where the loss is has been optimized is at 80 and approximately 130 or so. And so what this is telling us is that the mean is at 80, but the variance is at 130, the spread of the data set. So that's how you kind of interpret this graph of the function for minimizing mean squared error. Okay, and now let's also consider absolute loss. And well, actually, before that, one last thing that we might want to think about with variance is, we have this idea of H star, right? And so if we plug H star into our function, so this would be like r squared of H star, that's what gives us variance. And H star in of itself is just the mean. So in other words, what this is really saying is that the minimum, I guess the minimum value that you can get from squared error is the variance, and you get that when the H star, or whatever our constant, like the best constant prediction that we can use, is the mean. Of course, if you use another H, right, and that's not the mean, you're not going to get variance. You're going to get something slightly off. But if you use mean, which you've shown is the H star for the constant model with mean squared error, then that gets you back the variance. And if we go to absolute loss and we do the same process of taking the median, right, when we have H star, and we plug that back in for H, right? So right here, we wind up kind of getting something very, very similar, except of course in the realm of the median. And what we get is the mean absolute deviation from the median. So this is another type of spread that we're capturing with the data set, and it's the spread around the median. So what we're saying is essentially that if you plug for the mean absolute error H star in, then what you get is the mean absolute deviation from the median. So what would like an example of that be? Like if this is our data set right here, and we did these quick calculations. We did, 2 minus 3, and this is of course 3 here being the median. So and that was 3 minus 3 and 3 minus 3 and 4 minus 3 and 5 minus 3. Then that gets us 1, 0, 0, 1, and 2, 1, 2, 3, 4. So if we add those all up, we get 4/5, and 4/5 is the mean absolute deviation from the median. So what that says is, on average, each of our data points is 4/5 units away from the median. So that's kind of what we're talking about here. And if we look at the plot with our original data set that we were using from when the lecture started, this behaves a lot in a sense like the mean squared error. So right here at the corner, the very minimum, we have the median, which is going to be 8.5. So that's the median. But what's going on over here? Well, that's going to be the mean absolute deviation from the median. So we can this is just below 10, so maybe 9.7 or something. So this is now 8.5, 9.7. So at best, if we use the median, and that's what we get as our H star, then the spread for this loss function is going to be 9.7. So on average, each of these data points is 9.7 units away from the median. And of course, if we use any, that's for H star, if we use anything else for H, that 9.7 becomes worse, or worse measure of the spread, not as accurate. And then to just finish this off, the 0-1 loss is even less interesting to look at in terms of spread because we're talking about the mode. And so at best, all we can really talk about is how clumped up the data is. And yeah, I mean, that's pretty much it for mode. So, kind of what is this summary of center and spread? What is it that we're kind of getting from this? And what we want to think about is the connectedness between the loss functions that we've calculated and the H stars that we've derived from them. That is to say that each of these loss functions is trying to find different ways of describing balance points between the data or within a data set, because a balance point is a great prediction to make, given no other information. And when we have that balance point, we know something about the center of the data, but the way we calculate that balance point is by deriving some sort of measurement from each data point, or perhaps counting the number of data points on each side of this balance point. And so that information is now kind of baked in to this entire process, because in order to calculate that, you've got to know the distance or the amount. And so that's what the spread is kind of talking about, variance. And so these things are kind of linked together fundamentally. And it's important from like a theoretical foundations point of view to understand how these things kind of belong together and relate. So that's where we're going to leave it for today's lecture. Going forward, in the next one, we're going to kind of start to depart away from the constant model after we may do some review next lecture. But we're gonna be moving towards linear regression, and we'll start with simple linear regression, which means that we're going to have only one parameter or one variable that we're dealing with, and when we're dealing with just one parameter, we can of course look at linear regression in a two-dimensional plane. And so we're going to, much like the constant model, the linear regression model, we're going to have a line, and that line is the model, and we're going to try and find which line is best, right? It could be this line, could be that line, could be this line. There are infinite numbers of lines that we could draw here, but only one line is the best fit line, and that's the line that best fits the data. And so we're going to take the ideas that we've learned so far with the constant model and with mean squared or mean absolute error and mean squared error and all these other kinds of loss functions, and we're going to try and determine the best fit line for the linear regression model. And after that, we'll go into more complex modeling, linear regression in multiple dimensions, where it's not so easy to plot what's going on, but we can use these loss functions and the fact that we can differentiate loss functions to derive what would be the best, in that case, hyperplane. So that's kind of where we're going. And it's all the effort to try and make good quality predictions, create good quality models that can, accurately model the data generating process of our world. So And again, we're going to be following just a very simple modeling recipe. So this is an important concept to think about. Except now, instead of the constant model, there would be something like, linear regression model, and the loss function will be a little bit more interesting as well. And the amount of parameters will become much more interesting and complex as well. So this is where we're going. We'll leave it at that for now.